Hi, today I'll present online lattice-based abstraction of user groups. It's a collaboration between The Ohio State University, CNRS, and Grenoble Alpes University. Let's start by user data and motivate the need of abstraction. Nowadays, user data is everywhere. Huge amounts of user data are generated thanks to various sensors and unprecedented storage capacity. For instance, in the last 5 minutes, thousands to millions of new user content have been generated in different social networks such as Twitter, Facebook, and Instagram. But what is user data? User data is a conjunction of demographics such as age, location, gender, and profession, and user activities such as movie ratings, eating habits, political views, etc. This model forms a bipartite graph centered on users where there are demographics on one side and activities on the other side. The analysis of user data has various applications from population studies in the social science to market segmentation in online recommendations. Traditionally, analysis of user data is done per user. Individual-based analysis of user data, however, suffers from two drawbacks. Firstly, user data is sparse, that is, many attribute values are missing. Secondly, it is noisy, that means it may contain incorrect information. For instance, a professor cannot be a teenager. To tackle those inefficiencies, group-based analysis of user data has been proposed in the literature, which provides a summarized view of user space. Labeled user groups enable new insights, less sparsity, and less noise. All group members share common demographics and actions that describe the group. Two realistic examples of groups are shown here. For instance, a group in Twitter is teenagers in Lyon who have posted a tweet about their health. Also in Movie Lens, a movie rating website, a group is formed by young students who have rated movies of Woody Allen. However, there is a critical challenge in user group analysis, which is information overload. For a user dataset, there can be millions of groups hindering their effective analysis. It is a tedious task for an analyst to skim over all groups to find an interesting subset. We consider the challenge of information overload in two different stages of group-based user data analysis: investigation and presentation. At the stage of investigation, the analyst explores different options to make initial decisions and pick further analysis directions. A careful selection of groups to present to the analyst will provide a big picture that prevents information overload and enables effective investigation. The group space should be summarized in such a way that a smaller number of groups faithfully represents the whole group space. At this stage of presentation, which is usually in form of visualization, the analyst selects a group of interest and asks for details. The analyst will make up her mind based on provided details. A concise representation of those details in such a way that they carry informative insights will address information overload. A variety of approaches is proposed to tackle information overload for user groups, such as compression, interactive navigation, and constraint optimization. However, most of those approaches are lossy and require a priori domain knowledge in form of ontologies, rules, and constraints. Our solution is abstraction, a summarization approach in a lossless fashion. Abstraction provides a concise view of user groups with the ability to ask for details on demand. For instance, the group of young females who watched the movie Flicka and the group of males who watched the movie Schindler's List can be both abstracted to the group of drama genre lovers. Abstraction addresses both stages of user data analysis, investigation, and presentation. Rewriting multiple groups into a single abstracted group will summarize the group space for investigation and reduce visual clutter in presentation. So let's see what abstraction means in action. In the literature, abstraction is often defined based on domain-specific taxonomies which dictate the generalization process. However, such taxonomies are often handcrafted and therefore expensive to produce. Also, the abstraction functionality heavily depends on the nature of the taxonomy, such as its height and branching factor. We exploit the opportunity of using the user group lattice for abstraction. The lattice is automatically generated in the process of user group discovery, hence no input taxonomy is required. An example of a partial user group lattice is illustrated here, where, for instance, both groups of Californian students and Californian engineers can be abstracted to the group of Californians. So we discuss lattice-based abstraction in this talk. But how does this abstraction work? At the core of lattice-based abstraction lies the notion of quality. In user data analysis, quality is defined as a function of user behavior, which means that an abstracted group should reflect the behavior of groups it contains. Quality can be captured either as a score or frequency. A larger score or frequency can be assumed to be equivalent as higher quality. For instance, the group of young females who rate the movie Flicka with the score 3 and the group of males who rate the movie Schindler's List with the score 2.8 can be both abstracted to a group of drama genre lovers with average rating score of 2.9 while the quality scores are relatively the same. The same example can also be mentioned for the case of frequency. Based on the notion of quality, we define the notion of quality waste, which is the difference in quality between abstracted group and non-abstracted groups. Considering a sensitivity threshold rho for quality waste, we define maximal abstraction as the abstraction with less than rho of quality waste, where there is no other abstraction candidate which is more generalized than the abstracted group. That being said, we formally define our abstraction problem, that is, to provide the set of all maximally abstracted groups for n given input groups. To solve the abstraction problem, we present Augment, a framework that enables efficient lattice-based abstraction of user groups. The main focus in the architecture of Augment is on efficiency, in order to enable on-the-fly abstractions. Augment first produces user groups, then it generates some metadata for them. Last, it exploits metadata to obtain maximal abstracted groups efficiently. We describe each component of Augment as follows. The set of user groups is generated from input user data in an offline process. This one-time process is independent from Augment and can be done with different algorithms such as clustering, community detection, pattern mining, and team formation. While generating groups, Augment stores some metadata about each generated group. We store metadata in form of one-level abstractions. As only certain groups constitute a valid one-level abstraction, a huge pruning will occur. Finally, Augment takes a set of n groups and exploit abstraction opportunities. Any set of n groups should be verified for abstraction. Single abstractions are already computed and multiple abstractions, that means for more than one group, are computed using the metadata dynamically. Let's follow the process in an example. Assume following lattice is built for a given input user data with groups G1 to G8. Quality is computed for each group. For example, the quality of group G1 is 3.5 and for group G2 is 2.1. We compute one-level abstractions in the second step by respecting the threshold rho, that is equal to 1.5. For instance, the quality waste between G1 and G5 is 1.3. Note that we don't materialize the quality waste between G2 and G7 as its quality waste is larger than the sensitivity threshold rho. Then in the online computation, given a subset of groups to abstract, that is in this case G1, G2, G3, and G4, we can easily make abstraction decisions. For instance, abstracting the set G1 and G2 to G5 is valid as both abstractions of G1 to G5 and G2 to G5 exist in our metadata table. This is the algorithm behind the online abstraction step. Given an input set of groups G in, the algorithm iterates on all its subsets. As the number of possible abstractions is large, we consider a time limit parameter gamma to bound user waiting time. Hence, the abstraction algorithm employs a greedy best effort strategy to return the set of abstractions with the least quality waste within the time limit gamma. The algorithm favors abstractions of subsets with larger cardinality. Hence, even with a restrictive gamma, abstractions which contribute to group space reduction will be executed first. The algorithm favors abstractions of subsets with larger cardinality. Hence, even with a restrictive gamma, abstractions which contribute more to group space reduction will be executed first. In practice, we often set gamma to 400 milliseconds in accordance with productivity degradation limit defined in the literature. We evaluate the effectiveness and usability of AugMan in an extensive set of experiments. We use two user datasets, movie lens and book crossing. Both datasets have explicit quality scores ranging from 1 to 5. We validate qualitative aspects of AugMan in a user study. For a given subset of records in movie lens, that is ratings of Woody Allen movies, participants were given a set of abstracted and non-abstracted groups side by side. They expressed their preference on a 5-star scale, 5 being the most preferred, on the informativeness and representativeness of user groups for describing Woody Allen movies. The following figure illustrates results. Participants received various sets of abstracted and non-abstracted groups obtained from different group space sizes, which is the left chart, and sensitivity values, which is the right chart. In general, abstracted groups are preferred to non-abstracted ones in most cases, specifically in larger group spaces. By increasing group space size, we observe that the preference for non-abstracted groups decreases drastically, while for abstracted groups it stays almost constant. The reason is that participants can potentially make sense out of non-abstracted groups in smaller datasets, but when the space becomes larger, hence less manageable, the need for an abstracted view increases. Note that even in the smallest space size, abstraction is preferred as much as non-abstraction. Sensitivity threshold manages the tolerance of quality waste. The lower its value, the fewer the abstraction opportunities. We observe a sweet spot, that is rho equal to 3, where the preference for abstraction is highly contrasted in comparison to non-abstraction, that is 42% of difference in preference. When rho is equal to 1, non-abstraction is the winner due to the lack of abstraction opportunities. However, few abstractions have a high quality and capture a preference of 3.4 on average. When rho is equal to 4.5, preferences are not distinguishable due to many meaningless abstractions. Larger values of sensitivity obstruct the semantics of abstraction, hence participants can hardly promote abstracted groups to non-abstracted ones. We also evaluate the performance of Augment by considering various sensitivity thresholds and group space sizes. We measure the execution time after 20 runs. In the left chart, we vary the group space size from 10 power of 3 to 10 power of 7 and by fixing rho equal to 3. In the right chart, we vary the sensitivity threshold from 1 to 4.5 by fixing the group space size to 10 power of 5. Movie lens as a denser dataset requires more time for abstractions by increasing the group space size or relaxing the sensitivity threshold. Note that although the abstraction operates on the huge space of user groups, it is executed in average in 1302 milliseconds. This efficiency is obtained thanks to metadata table and proper indexing. In conclusion, we address the problem of information overload in the context of user groups in different stages of user data analysis. We propose Augment, a framework for an efficient abstraction of user groups based on the lattice. We validated different aspects of our framework in quantitative and qualitative experiments on movie lens and book crossing datasets. As perspectives, our immediate course of action is to build a visualization layer on top of Augment to visually present abstracted groups to analysts. The visualization should be able to present group abstractions and provide details on demand. In the future, we would like to consider feedback as a way to capture an analyst's interest and incorporate Augment in an interactive context. We also aim to address parallelism to enable more efficiency. All aggregation functions in Augment are totally algebraic, hence their functionality can be easily extended to shared nothing parallel data processing frameworks like Hadoop and Spark.